Hi everyone, we'll get started. Welcome to our CEIH, so that's the Commission on Excellence and Innovation in Health, Improvement and Innovation Showcase Series. My name is Tina Harden. I am the Executive Director of Clinical Informatics and Innovation at the CIH, and I'll be your host for today. This series has been exploring the topic of improving healthcare through machine learning and artificial intelligence. Before we start, I'd like to acknowledge that the land we gather on today is the land of the Kaurna people, and that we pay our respects and recognise their deep spiritual connection to country. We acknowledge the Kaurna people as the custodians of the Adelaide region, and that their cultural and heritage beliefs are still important to the living Kaurna people today. I'd also like to take the opportunity to acknowledge other people from other lands joining us today from around South Australia and perhaps even across Australia. A little bit of housekeeping. This presentation is being recorded, and during the presentation we ask that you keep your mics on mute. At the end of the presentation we will stop recording and go into question time, and then you're very welcome to turn on your cameras, turn on your mics and ask as many questions as you like. We really want to see your lovely smiling faces and have this as much interactive engagement as we can. For those not familiar with us, as I said, we are the CIH. We have a vision of together let's create better healthcare for South Australians. We lead innovation in healthcare in South Australia, and we really love to bring consumers, clinicians and other collaborators together to turn ideas into better healthcare. We do this by putting our imaginations to work, and we acknowledge that better isn't always excellent, but we like to measure and make sure that we're always having an impact and that we're driving change in the health system. So the forum today, or the series really, is about what if the big idea is connecting all the small ideas. And that's really the essence behind the Improvement and Innovation Showcase. It's about connecting people. If at the end of today's presentation you reach out to our presenter or in fact to anyone else who's joined us in the online session, then we've achieved what we set out to do. We've connected people and helped you find other like-minded and different perspectives from across the system so that we can all go and do fabulous things together. The Improvement and Innovation Showcase series is typically on Thursdays at about 1 p.m. And it sort of varies. We're turning them into sort of short series, but they're recorded and will be available to watch on our website. So if you miss it or you think it's relevant to someone else, please just let them know that they can join on. They can catch up on our website. We aim to keep it simple and share work that's happening across the sector, and with varying levels of success. So we're not just really wanting to showcase I guess exemplar projects. We're also interested in learning from others, so that true collaboration and sharing and building knowledge and expertise across the sector. As I said, we do focus on South Australia, but actually we really are encouraging sharing across other states and jurisdictions to spark ideas and spark that collaboration. In fact, if you have a story to tell or know someone that does, please get in contact with us. We're always looking for great topics or themes for our next showcase series. And we'd love to connect with you and engage and hear your story too and help you share it. So there's our email, cih@sa.gov.au. This current series, if you're only just joining us for the first time, well, you've missed all the others. So please, as I said, jump onto our website and catch up. We've had 4 in the series, and this is the final one. And I'm absolutely thrilled that we have Al-Saffar joining us. I'll introduce him shortly. And previously, we've had our very own data scientist in Bertram talking about developing diagnostic tools for general medicine patients with shortness of breath. We've been joined by Lucy Marsh-Smith from SALHN, the Central Adelaide Local Health Network, on AI's influence on healthcare, a disruptive force. And we've also been joined by Samuel Gluck from Northern Adelaide Local Health Network, sharing his story about natural language processing to predict hospital discharge and a case for implementation. So the fourth and final, as I said, today is Al-Saffar, data scientist from Southern Adelaide Local Health Network. He's going to be talking about statewide deep learning models for length of stay estimation at 0 hour of admission. So I'm going to stop sharing my screen now. And Alex, very excited to have you here with us today, and I look forward to hearing your presentation. I'm going to stop sharing and over to you.
Thanks, Tina. Let's get started. So I think I'm going to start by introducing myself a little bit more. Who am I? That's a shell command, by the way. So I have PhD from the University of Queensland, and I finished that in 2021. And that was about data-driven techniques for electromagnetic biomedical imaging. So this is a new imaging modality that relies on electromagnetic waves as opposed to the X-rays or the magnetic waves. So they had this device there. They were giving me signals look like this, and I'm supposed to be doing the magic and convert that into a proper image. Now, I have a patented neural network to do that, and the rationale behind that was it's extremely hard to build a mathematical model to figure out what's happening there, a lot of refraction, reflection. So that was the motivation for using deep neural networks. The results were profound, and because the best that they were hoping for is something that you could see on the radar of military or civilian things that you could see in the airport, blobs, that's all you could see on the screen. That's the limitation of the radar technology. But then I was giving them this image and they said, that's not possible. Like this defies the physics wave. So that's why it was patented. It came to my knowledge that last month it was made a US patent, which is the highest form. I had a bit of a problem there, so I left and, oh well, I started a new career in SA Health. So I'm full-time with SA Health since September 2022. And since then, I've authored, well, let's have a look. If I Z to work and if I run Tokay, right, I've authored 109,000 lines of code in Python and few thousands SQL and 7 lines of code in Julia. Well, 2 of which are blank lines and 1 of them is a comment. That's actually 4 lines. All of that is powering up my landing page. It was meant to be a place that hosts all the AI applications. So once you hear about, oh, here's AI model to someone build, this should be the place where you go to try it out by yourself. Not that I got much support for it. So at the moment, it's just pointing to everything that I built for myself. Today, though, we are focusing on just one of those. That is the length of stay model called LOS 107. So the concept here is that I have a 3 modules neural network to predict the length of stay, and we do that 1 second after the patient is admitted. People argue, is it too early to predict the length of stay 1 second after admission? And my argument is that you can delay it, but the value of your prediction starts to deteriorate. So if you predict length of stay 5 minutes before the patient is discharged, yeah, you're going to get high accuracy, but what's the value? So formally, the information is defined as the negative log of probability of an event happening. So if the event has 100% probability, then the log of that is 0. So that's how much value, 0 bits of information in your prediction. So my model works here at this time at 0 admission, where the value of this prediction is maximum. Right, so some people say, oh, let's predict the length of stay after the surgery is finished or something like that. Well, that's like half of the battle is done, so there's less and less value in the prediction. Okay, now, compared to the literature, some of them require unrealistic inputs, like they have to predict, the clinician need to know what is the DRG beforehand, and it's really unrealistic. This thing requires 0 input from any clinician. Performance-wise, it exceeds an anti-causal model that assumes the knowledge of DRG. So if God somehow told someone that this will be the DRG, that's still not going to happen, not going to beat this model. And this model works statewide, as we established earlier. So we're going to provide length of stay admission for every patient in SA Health or wherever EMR is deployed, at least, with 0 inputs, 0 efforts from anyone in less than 30 seconds. So by the end of this presentation, we'll have a look at the front end, which is just a dashboard that shows the prediction for everyone as we speak. So at any given point, we have something like 4,000 inpatients. So that's the scope of this model. Right, and then we have the leaderboard that will show both the performance of those models. So this is actually a huge number of models, one for statewide service, and they perform variably depending on how hard is it to predict the length of stay in a given service. Okay, so we'll see that by the end. For now, let's start with the data to train those models. My hammer is neural networks. That's where I did my PhD, and that's what everything for me is the nail that I hit with this hammer. And they're hungry for data. So one service is not enough. I need 10,000, something like that. That would be ideal. One service is not enough, and therefore I created something called a statewide service. So I group all the services that do something similar. So something that a service provides in RA and FMC and QEH, put that together in one bucket, and that will provide the training samples for one of the models. The grouping should strike the right level of granularity, because if we made it too generic, that will introduce a wild distribution and a lot of chaos. There will be little hope that the model will learn anything. And if you made it too specific, then there will be few samples that are not enough for training. So you have to strike the right level of granularity there. It's a trade-off between the group size and the coherency of the patients in that group. An indirect benefit of this is that the models that I built work statewide, so a lot of impact for whatever model we produce. This is the grouping that I've done. So here's a concrete example. If I say vascular, so one model for all the vascular patients, what does that mean? That model works for RA vascular / 040, QEH vascular / 057, and FMC IP vascular / VACSC. So we group those together, and that'll produce one model for anyone who is admitted here. And you do the same thing for everything else. Yeah, I did this, and all of this is based on evil string manipulation, because they have those characters in them, put them together. So there was zero corporate knowledge, zero clinical input that went into that categorization, but this is about to change. I'm now with the State Coordination Center, where people actually care about grouping those. And it's actually important, not just for this work, for every single machine learning model to be built, because the first question will be, where is the data coming from? And there you go. You need to group those services that provide something similar. Right. So that's the grouping. And then to train and test, I used everything from 2012 to 2023 April. So that's like over 1 decade worth of training data. And then I evaluated on everything beyond that. And I used a little bit of a trick. It's an exponential decay function that attributes less value for samples that are old. So the model doesn't get as much punishment for missing those, because the system keeps changing. And I don't want to dump the data that is old. So before COVID it was different world. After COVID it's different. Things change. Don't want to dump it. Just give it low value when you train the model. Here is my contribution to the literature. How is my work different from whatever you see in the literature? Number one, direct regression of length of stay. Every work that you see in the literature shy away from predicting the length of stay as a regression problem. Instead, they reformulate it as a classification problem, and they just tell you, oh, it's a short, it's a medium, it's a long stay. Meanwhile, my work has got no problem producing 4 hours and 55 minutes. Number two, loss functions that are promoting a reasonable risk-taking attitude. When I started building the model, I was training it using this loss function. It's called the mean absolute percentage error, and that's how much I penalize the model for making a prediction. And after I finished training the model with this, I got the following results that you see under y_MAPI, mean absolute percentage error. It was underestimating most of the time. So if you look at the correct length of stay, which is y, and the predicted length of stay, which is y tilde, you will see that it always underestimates, except for 1, 2, 3, 4, and 90% of the cases it was underestimating. So the correct answer is 3 to 1 hours, and it's predicted 11. And I was thinking, why is it always underestimating? And it turns out by looking at the loss function, turns out that the loss, the penalty that you get for underestimating, the worst case scenario is 100. So no matter what is the correct length of stay, if you just say that the predicted length of stay is 0, then you are 100% away from the correct answer. So the model figured out this tricky way of avoiding losses by just underestimating, while if you overestimate, then there is no limit on how much punishment you get. So the more you predict length of stay, the more far away you are from the real one, the more loss you get. So you can get 10,000% off by overestimating. So that's the model was always underestimating. So to solve that, I created something I call the symmetric mean absolute percentage error, where the loss function penalizes the model equally for overestimating and underestimating. So if you can see everything here on the right, then the worst case scenario, if you underestimate, is that you're going to get a penalty of 100. And if you overestimate, then the penalty will asymptotically approach 1 as the predicted length of stay goes up to infinity. So if you go here all the way up to infinity, then that curve will go up all the way to, here's an asymptote, 100. So the model will see, okay, well, if I overestimate, underestimate, it's the same thing. So the result was reasonable risk-taking attitude, which is what you can see here. So this is the loss after I introduced the second loss, the performance, the predicted length of stay, after I introduced the second loss function. As you can see, compared to the correct, this is the ground truth, and this is the prediction, it overestimates, underestimates 50%. So everything that's highlighted is an overestimation, which is about half of the time. Right, so that's the second contribution. The third one is the elegant handling of ragged data with autoencoders and RNNs. One of the most important inputs to my model is the historical ICD-10s. Now, those are little codes that are variable, and it's not clear how do you feed those to a model. So this is how I handled it. I built an autoencoder that converts every ICD-10 to a latent space representation. And to prove that it's actually meaningful, latent space representation, was doing some playful things. I took a few codes and I fed that to my autoencoder. So this is an ICD-10 code, M651, and I encoded that, and I got some latent space vector like this one, such as 5-dimensional representation. And then I got another code called H600, and I encoded that, and I got another vector. Now we have 2 vectors, subtract a vector from a vector to get another vector. Now, inverse transform that back into the original ambient space, you will get L574. Now, in English, the first code was actually infective tenosynovitis, and the second one was otitis externa. The third one was cutis laxa senilis. I see those for the first time in my life. It roughly means an infective disease minus a malignant part is equal to loose skin, medical condition. Another example that I got was a hemorrhagic stroke minus a motorcycle accident type of ICD-10 is equal to a sharp object type of ICD-10. So it kind of makes sense. That's how the computer understands those ICD-10, the neural network. Okay. So this is just to prove that's meaningful. The trick is common in the literature. You go from ambient space to latent space. You do arithmetic, you go back to the ambient space. Here is the full architecture. Let's go through this bit by bit. This is the patient identifier. Once we get that, we pull all the data from the database. And we get the following: a few categorical variables like gender, race, admit, source, admit type, and a few numerical variables like the age, admission hour, admission day a week, average visit count, number of visits so far. Those are easy to handle. And then most importantly, the ragged data, the historical ICD-10s. Now I put this sign here to indicate that this is a ragged dimension. We don't know how long is this dimension. Everyone has different number of historical ICD-10s, could be 1 or could be 0, all the way up to the sickest person in South Australia who had 150 historical ICD-10s. So I ranked everyone in South Australia, and that person's actually alive. Anyway, so you feed the historical ones up to that visit. And the way we handle those historical ICD-10s is by one-hot encoding, very classic. So that will convert them from those English things to 1001, things like that. And keep in mind, we're maintaining this irregular dimension. We haven't solved that yet. So I just did one-hot encoding. After that, I feed it to the autoencoder that I've just mentioned. This is the autoencoder, and this is trained separately, independent of everything else that you see here. We train this autoencoder, and then we come to do the rest of the work. And here's the big idea. because the population of ICD-10s is finite, it's around 40,000 codes, and I will never see a code that I've never seen before, then the risk of overfitting and memorizing is non-existent. So I made this a really big model. It has 11,000 parameters, and knowing that there will be no overfitting because there's no new ICD-10 at runtime. You train this separately, and then you can dump the decoder. It's not useful. We just use the encoder. So that'll take us from the 71 dimensions, which is that you see here. It comes from the one-hot encoding, all the way down to just 5 dimensions. So instead of this very sparse representation, we get a dense representation like 0.23 minus 0.54 and things like that. And we still have this ragged dimension until you feed it to the RNN. That will kill this and convert everything into just one vector that captures everything that we know about this patient historically. This gets concatenated with the data that's coming up from the other branch, which is this branch. Things that get concatenated, a little bit of numerical pre-processing like clipping and standardization, one-hot encoding. Okay, so you get just one long vector that gets fed to a multi-layer perceptron, which reduces everything down to just one number. That is the length of stay in hours. Here's an expansion on those neural networks. So this is the multi-layer perceptron. This is the RNN, and this is the encoder, and this is the decoder. So I've been abstracting them to boxes, but this is the full architecture. Okay, right. So that produces, here's a sample of results, and I always like to cherry pick the good ones. So let's have a look. Here is an example where the correct length of stay was 130 hours, and I predict 127. All right, I was 3 hours off. That's just a good example, a very good example, I should say. There are terrible ones. Here's the full scenery. This is a way of showing the performance on 3,600 cases, and here's the way I show it. I plotted the correct length of stay as the green line, and I decided to go on the y-axis and put the length of stay relative to the correct one. So if you divide the correct one by itself, you get 1, and that's what you see here, 10 to the power 0. And I decided to put everything on the y-axis a logarithmic scale because it's wild. Right, so that's the green line. That's the correct length of stay. The orange is the predicted length of stay. So the closest the orange to the green, the better. So that means that's really good here. I'm very close to the green, and this is the worst case scenario. Here's the worst example ever, where it goes all the way up to 10 to the power 2, which is 100. That means the correct length of stay was 100 times more than the correct value. I was looking at this example just out of curiosity. What happened there? Turns out someone was admitted for 5 minutes and then was discharged. And then the model says 100 hours. Yeah, you're off by that 1,000% off. And here's another example, it's the opposite, where the prediction is 1/100th of the correct one. Yeah, but ignore those because they are like outliers. They happen like 1% of the time. So this is where we have the majority of the cases. Okay. I've developed 2 packages. One of them is called SAML while I was working on this. So SAML SA Health Machine Learning. It's meant to be developed by the community. That's the hope. Just kickstarted the process. Yeah, so everything is open source. We're happy to share this with, and this is the length of stay package. Everything is pip installable. We're happy to share it under very rather permissive license. So long you don't make money off of this, then we're happy to share this with you. Now here's a demo to the front end. All right, let me jump to, yeah. This is the dashboard that shows all the results live, 4,000 inpatients as we speak. Right, and you can see here, we have LOS so far, LOS expected, LOS standard deviation, that's how much confidence we have, and then the model. I don't have the neural network for all of them, so you see here's a neural network for some of them. We'll talk about that later, and then the quantile so far and the quantile expected. So that puts some context because the number of hours varies across services. So 6 hours is forever in the context of, I don't know, dental surgery, but in context of rehab, 6 hours is nothing. So to put everything into perspective, I had to build the quantile. So this is in the 90%. They look like everyone, or there's 2% that's like top 2% longest staying with respect to the distribution of that service. This is the historical ICD-10s of that patient, but you don't worry about that. That's all gets fed to the model, and based on that, you predict the length of stay. But this is the advantage that the model has over a human looking at the patient. Yes, that the human has a live view of the patient, but the model has the advantage of looking at everything historically. Right, now you can slice and dice this model in many, many ways because we want to focus on people of interest. Some of them are not of interest. So if I sort things out by the LOS so far, so you see the longest staying person in SA Health is this dude, 47,000 hours, 32,000. They've been admitted for like 8 years or something. And they are very famous people. So if you go to those divisions and tell them about those people, well, they know them very well, and it's pointless to make any prediction about those. But maybe we care more about the people who were admitted recently. Most of those are mental health, and it turns out that this is the actual hardest service. I thought it's gen med, but it's not true. Right. So the point is, you can slice it in ways that you can focus on people of interest. So here's one slice that says recently arriving expected long stayers, or arriving within 24 but expected to stay at least 7 days. Many different ways of focusing on people of interest. So this is the mother table that can be derived in so many different ways. Here is an important caveat. The predictions made is for the current service only, not the entire episode of care. So my atoms were the CV3 services, some table in the back end of EMR. To produce the total length of stay, we're going to have to, well, I made something called the patientogram that will show you how the patients flow across services. So here are the services. Say you were admitted to somewhere in general medicine, then I have the model that predicts length of stay for that service alone. But after you finish that, it's not necessarily that you will go home. Well, there's what? There's 59% chance of going home after that service. And then there is some probability that you will end up here. But with higher probabilities, you'll end up going to a different service. And then from there, you go to a different one. And you keep bouncing back and forth between services until you eventually reach out to one of those, or they call them terminal nodes in graph theory terminology. So to produce the total length of stay, what I need to do is multiply out, add the length of stay that I got for this service times, plus the length of stay for the next one, multiplied by the probability of going to that place in the first place, plus the length of stay to going to the next destination, multiplied by the probability of going there, and so on. It's the same formula that they use, it's called decision tree, that they same formula used by all those insurance companies to give you the quote. All right, so we have the plan, you know how to do it properly, just a matter of adding up the numbers and expanding, well, forcing this graph into a tree structure and expanding it like 8 steps, maybe 7 steps down the way to get the length of stay for the entire episode of care. Right. Now, what else do I have? I have a leaderboard that shows the performance of each one of those models. Now, as I said, the services vary in complexity. So I've put a field here that shows how hard is it to predict length of stay. And if I organize by that, actually, you will see that the hardest service ever is RA acute mental health, followed by MIL IP Gen Med, followed by FMC IP acute mental health, RA neurosurgery, and so on. So those are really hard. There's so much chaos in the distribution of length of stay, and I have a proxy metric for that. It's the SMAPI median. Think of it as the entropy of the distribution there. If you organize, let's have a look at the easiest services ever. That should be RA hyperbaric QH radiology, dialysis, those are the easiest one. Right, now, one of my best models was raw neurology 027, and that reduced the entropy from 257 to all the way down to 50. So you see, even though it was a really, really hard service, but look how much improvement you have after using the model. So the model will be 50% on average away from the correct length of stay, and that's after 1 second from admission. And those results are based, this is the height of transparency. I can't report it in a way more transparent than this. This is unseen data from the period 1st of September to, well, 1st of December. So this data has not contaminated the training process in any way, shape, or form. It's literally unseen. And things are bound to get better as we move away from here, because remember, if I just Z to SAML and BAT, the enterprise file, once this gets improved, as I told you before, there's zero clinical input and zero corporate knowledge that went into doing this grouping. But this is about to change. And once this is changed and we get a better grouping, more coherent group of people, then the results are only going to get better with the next iterations. And by next iteration, I just need to Z to 107 and fire the logic, and that will retrain, well, starting from downloading new data and training it, producing all the new models, all the way down to the figures that you see in the presentation. They get updated automatically. Okay, but let me stop that for now, because that will take a whole week to finish. It's pathetic that I don't have supercomputers. Now, while I'm here, let me Z to the checkpoint, and this training process eventually will be producing, oh, sorry, Z checkpoint, checkpoint 1, okay. It will be producing models for all of those statewide services, and in each one of them, so ZV Oncology, for example, we have 10 models. Let's read out the names because I like that. We have those 10 neural networks named Abstract Pivot, Baked Echelon, Covering Coordinator, Dry Shack, Giant Shackle, Merciless Moat, Naive Digraph, Navy Gauge, Tailnet, and Slow Cliche. Those 10 models, although trained on similar data, they converge to a different local minimum, therefore producing different answers. The answer, the standard deviation of which is our metric for uncertainty in the prediction that we make. So if they all agree on one answer, it means we're really confident that this is the correct length of stay. If each one of them say something different, then we probably don't know what we're doing. So that's how you see the estimation of uncertainty in the front page, which is, yeah, which was this column here. LOS STD, this one. Okay, I think that's the end of the demo. What else do I have if I need to jump back to the presentation? That's the web app demo. This is the full picture of how we started everything, from problem formulation all the way to the model, going back and forth. Sometimes you finish building the model and you realize there's something wrong, all the way back to the drawing board. And I realized this is endless work. I could be stuck there forever. And everything that you see on the right was never touched, which is like productionization and bringing it to the users. So I realized we should stop here, declare this is a version. This is what we have now, push it to production, and then we can iterate on the next version. Applications so far. I'm going to quickly go through 2 applications: system capacity prediction and complexity indicator application. So I'm going to jump again to my landing page. The system capacity estimation, working on modeling the whole SA Health patient flow process, and the length of stay model will help us predict how many beds will be available at any given point in time. There's complexity indicator. As the name suggests, we want to be able to know which patients we should be focusing on based on a few structured data that will be generated through queries, unstructured data that will be generated from large language models. So everything that you see here, ITO, EPOG, special nurse, ACAT, and consults, is coming from questions that we predefined. Like here's the question about ITO. Is there an inpatient treatment order ITO? Answer with yes or no. And here are the relevant documents in which we think the answer should come from. Question 1, question 2, question 3. All of those get fed to a chatbot that will generate the yes/no answers. And that will be translated to one of those ticks and crosses that you see here. And then there's another input that feeds to the complexity indicator, which is the risk of a long stay. So which one of those patients is expected to be a long stayer? That will get you another tick or a cross. So you see all of that work boils down to just a cross or a tick into this piece of work. Yeah, so that's an application, and I put here ellipses to indicate there are more to come. I think the takeaway message from here is that length of stay is very versatile. It's like tomatoes. You can stick it anywhere. It works. That's why there are thousands of papers on length of stay since the 80s. Here's just an acknowledgement of my collaborators. Those people, if I have any clinical or corporate knowledge, is thanks to those people from SALHN. And from the commission, I'd like to thank Tina and Ian, because this work was parked aside for over a year, and then they really championed pushing it forward to production. So I've been working with Ian to validate everything over the past few months. So that's my acknowledgement to the collaborators, and I conclude.
Alex, what a fantastic body of work. There's a website called Information is Beautiful. I think you've just made data science beautiful and very, very exciting. I'd like to take this opportunity to thank you for your time in pulling that presentation together, and obviously for your enthusiasm, passion, and intellect in really being able to look at some of the wicked problems we've had in healthcare and put a completely different lens on it. And I think shift some of the goalposts for us. So I'd like to take this opportunity to thank you, and thank you for your time in coming to present today.